And guess what both cities have in common? Both cities are ports for their respective organizations or respective countries, meaning container ships pull up there daily. And we're going to be talking about containers, so I'm going to walk you through some of that fun stuff real quickly. So you can see right here that we basically are at the Golden Gate Bridge. We're hanging out in San Francisco. These folks here, these are great images, by the way, built that bridge. They had to walk up and down and build it. So some amazing things had to occur just in this local city here to make things happen. And of course, we're trying to build software at scale. We're trying to build amazing things ourselves. So that's why I like these images. So you can kind of see the Golden Gate going up there as an example. You can kind of see another image of it being built. So it's just some kind of amazing what has occurred here. But really, this town was formed from transportation of goods. And the shipping container fundamentally revolutionized shipping around the world. Everything was in a uniform size and shape. And essentially now, depending on what port you go to, they have no humans involved in moving container ships to and from ships now. So specifically in the Netherlands, I actually met with a shipping executive recently, oddly enough, and he's like, yeah, we're all robotic now. There are no humans on the yard. In Singapore, I met with their port authority to talk about Linux containers, and they're like, yeah, we're going to basically make everything robotic here too. So things are really changing in this universe for these shipping container ships. And things are really changing in our universe because containers allow us to more easily move across clouds, to the cloud and across clouds as an example. But the challenge is you want to make sure you don't blow the thing up and cause a massive problem. This is actually a fire on a container ship in San Francisco as an example. So you're going to see a lot of these images as we do this. Docker made Linux containers famous. And again, it's that uniform size and shape in the case of the physical world. In our case, in the software world, is the uniformity of the packaging and a codified way of describing the packaging, programmatic, if you will, as opposed to, let's say, an old email or something of that nature. We can, of course, put these things nicely together into a cloud architecture. Running them in something like a Kubernetes is a good example. And we want to put our Java in one of these guys. We want to put Java in one of these containers. And of course, it feels like we're going to lock poor Duke in jail. And what we don't want is for him to blow up. Because by default, it goes boom, okay? It does. And so we'll show you that. The weird part is you probably won't know why it goes boom and when it goes boom. It actually does it very consistently under certain circumstances. And here's the worst part. You don't get any logging. You just don't know. You just got killed. And you have no information about that event, unless you know about Linux kernels and internals. Okay? So what we really want is Duke living happily in his container, hanging out on the beach, and of course we have a nice seal here because we have the sea lions down at the bay, down the pier. So the container concept actually has been massive wins for developers as a whole. It gives us again that programmatic, that codified way to actually produce a Linux stack. And basically, if we build our JVM-based application on top of a Linux stack, we identify all our dependencies in a nice codified way. We know exactly what's going on there. It helps us address the "it works on my machine" issue, because how often does that happen to you? This happened to me recently with a continuous delivery of a SaaS product. Okay, so literally the engineering told me, oh, but it works on my machine, and it's a SaaS product through the browser. And it didn't work on my machine. It was a really funny conversation. Everyone had to laugh about it, and literally it was true. We got on a shared screen thing, and it worked on his screen, not mine. We couldn't figure out why. So it helps you match your dev environments to your production environments, and it does fundamentally help address that, but that's actually where the problem gets generated. You assume that you have certain resources available to your container on your laptop, but when you move that same container to production, there's different resources available. And the JVM does not respect container-based resources at this moment in time. It assumes it has access to the full host, okay? And that's where things get kind of crazy. So there'll be lots of pictures of container ships in here as we go, and of course, container ships failing. Because what you don't want is it to crash and burn, okay? So we'll keep going here. The concept of virtualization, we started this journey of virtualization a long time ago. I've actually met several people at Java 1 who have yet to move to the virtualization world, but now we're telling you, forget virtualization, just go straight to containers. But the real wins here are the container is vastly smaller, and it also has a nice interface, if you will, in the form of the Docker file. It's easy to specify, it's easy to actually identify, and so it is nice to have that concept. And if you actually remember the keynote that gave Docker birth, so it was a 5-minute lightning talk at a Python conference about 4 years ago that gave Docker birth. From a 5-minute presentation, they lit the world on fire. He showed the world Docker build, Docker run, and people's minds were blown. So if you actually remember back to that first instance you did your first Docker build, Docker run, wasn't your mind blown? You're like, holy crap, I just ran whatever Linux with whatever I want on my laptop, my Windows-based laptop, like that. And it started in seconds, as opposed to getting a big old VM launched, right? Getting it baked out correctly, getting that VM started. So the container concept really has changed the game for developers fundamentally. Now there's lots of pros and cons associated with these containers versus Linux machines. You've got to keep in mind it's not a real virtual machine. It's certainly not that at all. It's just a process. It's a process that's highly governed through various technologies like C groups as an example and namespaces. And because it's a process, if you are at the host level, you can see all those little containers yourself. Now, each container can't see all the other containers, but the host certainly can because they're just processes. So if you do a ps-ef on the host side, you will see these things. So you got to keep that in mind. It's not a real hard virtualized hypervisor-based solution. Yeah, you can break out of the container also, and that has to be monitored to some degree. Okay? There's history of containers is actually important. I mentioned earlier that Docker was born in this little 5-minute keynote, and a lot of people think that was the moment when it happened. And actually, containers were a long time coming, a long time in formation, many, many years and lots of innovations. We had things in Solaris, right? We had things in AIX. We had different things in different flavors of Unix. And then, of course, things like SE Linux, which came out of the NSA many, many years ago, where they wanted to be able to sequester and compartmentalize Linux processes, identify what a process had access to, like it only has access to this memory, only has access to this file system. All those concepts bled into the world of containers. So it's been a long time coming. It's just that Docker made it popular and made it easy for developers to actually give it a try. Okay, now we have things like Kubernetes, which are making it run at scale, and that's super awesome also, as you saw in many presentations this week. That is the way the industry has moved, if you will, right? So Oracle, IBM, ourselves at Red Hat, everybody's basically saying, yep, Kubernetes is the de facto standard for running your Docker containers at scale. Now, here's the problem with that history that I just gave you, and here's really the crux of the problem. Containers really got popular just a few years ago. Java was born a lot earlier than that, okay? So Java was built from 1996, and I even have the little tumbling Duke there, the little animated GIF. I guess, let's see if I go back and come back to him. Will he animate again? Nope, he's not going to animate anymore. I had to find him. But you should remember Duke from that era. If you started programming in 1997, 1996, you got the little tumbling Duke in your little AWT-based application, and that was it. Java applets were the thing. But Java pre-existed this whole world of containers. Therefore, it does not understand the world of containers. And it still doesn't to this day. And therefore, it might fall over and die, okay? So, the challenge that containers fundamentally address, if you guys don't mind me doing this introductory stuff, I know you guys do a lot of Docker already, but it addresses the stack definition. It was super easy for you to say, hey, it's Java's portable. If I build Java code, it just runs on the JVM. But it turns out all JVMs aren't created equal. They come from different vendors, but they also have different versions. And just a simple micro patch version on a JVM could blow up your application. I've seen it happen. So yes, it's all 1.6 dot something, but the dot something actually really matters for a lot of applications. I've seen it actually kill apps before. Not to mention, you have all the other things to be configured for your application. It might be yum install this and yum install that at the Linux level, but it might also simply be, I got to configure this JDBC driver correctly and get it loaded onto the system correctly. And I have to, of course, have things like maybe JMS queues or other aspects of configuration. And the nice thing is the Docker file helps you codify all that. Again, it makes it programmatic, makes it codified, it means you can check it into source control. And then, of course, you can run it and test it accordingly across multiple workstations and across multiple production machines. Am I talking too fast, by the way? I talk really fast. I'm sorry. But the concept of this concept of what is your stack, we did this before. We did it with email back in the day. This is also back when we used to email people all the source control, source for source control. And you're probably thinking, what? And actually, people still do it to this day. So don't raise your hand if you're still emailing the code base back and forth across developers as source control, but it's happening now, okay? So just think about it. The whole code base was emailed back and forth, and let's say we got a little smarter, we just emailed the configuration stack. We emailed it to the QA team, please set up the application this way. We emailed it to the production team, please set up the application this way. But we tested on our workstation with Windows and this version of Java and this version of a JDBC driver with MySQL instead of the Oracle that we use in production. But in production, we use a Red Hat Enterprise Linux, and we have the Oracle, and we have everything else. Things don't match, and that's where things went sideways on us. And this is really what Docker and Linux containers fundamentally address. It really helps support this solution. And again, the Docker file is where that gets codified. Okay? All right, we got to keep moving fast here. Now, shipping containers, of course, move around the globe, and because of uniformity, it means you can move them from place to place, and that's really the goal here, to move them from cloud to cloud. So behind the scenes, what is really occurring? Behind the scenes, we're dealing with these things called C groups and namespaces. These are actually at the Linux level. They have really nothing to do with Docker at all. Think of Docker as nothing more than just a really cool API and user interface, developer experience on top of all this stuff. You can write your own bash shell scripts to manipulate these files directly. And you can interact with these things directly if you choose to. And if you're a hardcore Linux kernel propeller head, you would. That's not really me, though. I'm a Java programmer. I'd rather not deal with hardcore Linux internals if I don't have to. But in this case, you kind of need to know a little bit about them, because what Docker is manipulating is specifically the C groups around memory and CPU settings. When you basically say, I want to constrain memory for this container or constrain CPU for this container, it's doing it with C groups. Okay? And again, you can do that directly. And namespaces, of course, for dealing with things like the process identifiers and other resources. But that one in the middle that basically says limit in bytes, that's the one that basically causes all this to go sideways on you. Because here's what happens. In your Docker container, in your Kubernetes YAML, you say, I want to constrain this container to 400 megs of RAM. Okay, my Spring Boot app, my Vertex app, my Wildfly Swarm app, my little Java application gets 400 megs, and that's what I want it to have. And you really need to specify that, because otherwise, why are you living in container land anyway? You need to specify the memory limit and the core count limit, because that's really what it's going to give you to scale across the cloud. Okay? So in other words, you specify those things, and then if you move from box to box to box, right, in theory, you have access to those resources. And if you're really clever with Kubernetes, it'll schedule that container onto a node that has the capacity for it. Okay? Therefore, identifying your memory and identifying your core count matters. But when Docker is doing this specifically at the C groups level, C groups will kill your Java virtual machine if it goes beyond its limits. If it goes beyond the memory limit, it just kills it dead silently. You don't know what happened. All right, so you got to be cautious to how you run your Docker container. It could be in a little thing like this, another fun image. And so do you want to run a little bitty boat there? And we would say you really want to run this across something like Kubernetes. Kubernetes allows you to deal with containers at scale. And so if you think of it, you could actually run a bunch of those little boats with their little container in them. And people were doing this. So for those of you, all you raised your hand with just Docker, but haven't looked at Kubernetes, you're kind of in this path, right? You're like, okay, I got this Docker thing running here, and that Docker thing running there, and that Docker thing running there, and we shell scripted it, and somebody knows how to make it run. Okay, cool. I'm with you. That's kind of what I would do too when I'm hacking. But you can also do this at a greater scale, and that's really what Kubernetes allows you to do. Kubernetes, of course, means helmsman in Greek, and meaning it's the ship's pilot, the ship's captain, if you will. It's the one that's steering that big old container ship full of all those containers. And the idea being, and by the way, OpenShift is the Red Hat enterprise supported version of Kubernetes. But this diagram basically talks about the fact that it's going to manage that cluster of containers for you, right? Containing all kinds of crazy stuff, PHP, Python, Java, MySQL, Postgres, all those different things, and it's going to manage them at scale, and should anything actually bad happen, like let's say a node dies, a whole server dies, it'll just reschedule those containers across other nodes. Okay? All right. I got a few odd more minutes left. Here's why this fails. In the case of developing on a little tiny developer workstation, you can see there where we have 8 gigs of RAM and 4 cores. So I have put Docker for Mac down, I put Docker for Windows down, and I gave that virtual machine, and depending if you use VirtualBox or use xHive, use Hyper-V, it doesn't matter which virtual machine you use, I gave it 8 gigs of RAM and 4 cores to work with, and that's where I build my containers, that's where I Docker build, that's where I Docker run, it works, it seems to work okay. The problem is when you move it to the big production machine that actually has a lot more resources than that. And the problem is, specifically, Java sees all the resources on the virtual machine or host that it's living in. It doesn't realize it's living in a container. It is C groups agnostic or C groups ignorant. It just doesn't know. So it will over-allocate memory. So you can actually write this as a simple test. You can actually just go into Java. You can just try these tests, and there's a bunch of tests here in some of these slides, and basically say, hey Java, how much memory do you think you have? And it'll tell you all the memory on the host that it sees. What's your core count? All the cores on the host. It has no clue that it's living in a container. Now this is something we're working with on the OpenJDK team to fix, and there's some, I'll mention those tweaks that are in there, but it's still imperfect. I actually had a long discussion with the OpenJDK team. They thought they fixed it, but they didn't test it in a Kubernetes context, in which case they fixed the wrong thing. Also it should be noted, if you're familiar with Linux, free also fails. So Linux commands themselves also fail. They're container agnostic or container ignorant. So you got to keep that in mind too. You're like, oh, let me type in free. Maybe that'll tell me how much memory I have. Nope, it tells you all the memory on the host again. What's that?
How is Docker a container if it doesn't contain?
Docker is the API and developer experience for containers. Linux containers, of course, are part of C groups and namespaces, and they are just processes running on a Linux host. So there are aspects that leak out, if you will. And so Java was built long before containers, and it tries to grab more resources than it has. So you might have this situation, another topsy-turvy situation. Okay, who uses those APIs? So those APIs I just mentioned that I said just type them into your JVM, write the code, and try it. Guess what? Things like your Tomcat use those APIs. Things like your Wildfly use those APIs. Vertex, they use those APIs too to make calculations around how much memory should we allocate, how many threads should we put in our thread pool. Now Tomcat actually has a fixed thread pool count. By default, I think it's 200, but you can tweak it, obviously, and you should. You definitely need to in the context of living in a container. But by default, it's going to try to grab 200 threads, and 200 threads take about a megabyte each on a 64-bit JVM. So you now have lost 100 megs of RAM in a 400 meg container, just to threads you can't even use because you only have 2 cores or 1 core. You got to think about those kinds of problems. So this all is a result of JVM ergonomics. This is a page you can actually go access, and it'll tell you what the JVM is trying to do by default. Is it running in hotspot mode? Is it running client mode, server mode? Is it trying to do these different things and make smart calculations? The problem is those smart calculations were based on a world before containers. Okay, so it's trying to make good decisions about those things. And let's talk about memory very briefly. A lot of people think if you're dealing in a Java universe that heap is the answer, and it's not the only answer. So this isn't one that gets you. People get smart. They're like, okay, I know that I've constrained the container to 200 megs of RAM. I'm going to tell my heap size 200 megs. That's not going to work. Okay? Heap is approximately 50% of the memory used by the JVM. About. That's the rule of thumb we like to tell people. And so if you, in fact, you have a 200 meg container, you need 100 meg of heap, not more. So XMX needs to be no more than 100 in that context. So that's one that actually I've seen burn some people. They thought they fixed it, and they really didn't fix it. And again, the worst part is it blows up in production. It doesn't blow up in your laptop, right? It eventually just dies, and you don't know why. This happened to me recently, and a group of engineers at Red Hat. We had an application shutting down. We couldn't figure out why. And turned out it was this problem, okay? So this is what it looks like if you have that problem. All hell breaks loose, okay? So there's a workaround specifically. If you use the base images that we provide out of Docker Hub, and you can see there's one from the Fabricate-based image there, the OpenJDK image, we actually try to put a bunch of scripting into the build process that basically says, okay, if you in fact have constraints on your container, meaning you've actually specified that in the YAML file for Kubernetes or with Docker and with the Docker run command, you actually said, okay, it's fixed to 2 CPUs and it's fixed to 400 megs of RAM. Then we actually have scripts that go into the cgroups changes, the file system of cgroups, and grab the data out of them and apply those JVM commands accordingly. So in other words, we start the JVM with the right XMX. We start JVM with the right settings. So that's important to note. And I'm out of time, so we got to keep going here. This was patched, by the way, in 1.8.131, but it's imperfectly patched. That's what I mentioned earlier. So it's also fixed in Java 9. When I say imperfectly patched, it's because you have to remember you got to unlock experimental options. So it's not by default. You have to say, oh, I need these experimental options where I need to be smart about the specific memory allocation based on cgroup. So you kind of see it right there. You can see where it says use cgroup memory limit for heap. So it does work. I've tested it multiple times. But if you don't even know the flags exist, you're kind of screwed. That's why we're doing this session, okay? Now, core count. Here's the nice thing about memory count is the worst case scenario. It will blow up and die, and it silently fails. And this, I'm talking silently fails when users are just using the app, because users are adding things to their shopping cart, which uses heap. Next thing you know, it dies. Why did it die? I don't know. You don't get a log, okay? Because the kernel kills it. just kills it dead. So you don't even get a log in that case. So that's why this matters so much. Core count, though, is not as vicious, okay? Core count basically says, fine, if you want to try to think you have 200 threads in a thread pool, but you only have 1 core to run them on, that's tough for you. It just means you're gonna run slower, okay? It doesn't at least kill your process. It just ignores those extra requests to the core count. You can see we have the 4 Docker run commands specifying CPUs there. The Kubernetes uses that second option, so that's good to know. That's not using one of the other options. The Kubernetes uses the second option there. And the JVM only behaves properly with the 4th option, though. So, again, this is one of the ones where the team was like, we fixed it! And I tested it, and I said, no, you didn't. I didn't know. And we had to go back and forth. And then finally it said, we had different Docker run commands. They were using Docker run number 4, right? And I was using the Kubernetes one, which is number 2. And it really took about a week of back and forth before we realized we were using different Docker run commands. It does work in the case of number 4, which no one uses. You know how what number 4 does? It pins your process to specific cores in the actual machine. So if you have a 4-core machine, it pins it to 0 or 1, and in this case, let's say I specify 0 or 2, it knows that's 2 cores, you get 2 cores. You can't do that in a clustered environment, right? Especially with containers that might move back and forth across nodes. What, everybody is on 0 and 2? That wouldn't work, you know? So it was kind of a funny discussion when we realized we were kind of talking across purposes, okay? So you want to map those CPUs into Java, and you can kind of see what the recommendation is here. Use the serial GC if you're dealing with a sub 2-core scenario, and that's fairly common in a container world, right? You often, when you're living in a container world, you're going to constrain that process to about 2 cores on a regular basis. You don't want to give it 18 cores. As a matter of fact, you'd only have that many on the production machine anyway, and it's going to be hard to schedule across the cluster. So often you give it about 2 cores, and in the 2-core world, parallelized GC may not be the best answer. But you got to think about that, along with all the thread pools that you're also going to be running in your Tomcat or Wildfly, et cetera, WebSphere, WebLogic. Is that cool? All right, almost done. Again, the CPU set was patched, but don't use CPU sets. So now, I want you guys to now see a bunch of demos of these concepts, and Raphael's going to walk us through those demos, and I hopefully given him enough time. Is that cool?
Yeah.
So now you get to go do the fun stuff. I was the boring part. Is that cool?
Okay, so let's start playing a little bit with Docker so we can have an idea what really happens with a Docker Java application inside Docker. So I have here Docker running locally on my machine, but I also can use Docker machine to specify, to create virtual machines to test. So I have here one Docker machine created inside VirtualBox that I can show you here. This machine called Docker 1024. It's because it has 1 gig of memory. Okay, so what I'm doing now is pointing my Docker environment to this machine, Docker 1024 with 2 CPUs. Okay, so just to show you something, let me SSH on this machine. So if I do a free-8, it's a machine with 1 gig. But let's run a container inside this environment. So let me call it Docker run --rm because I don't want to reuse this machine. Incremental interactive terminal, and I will run a Fedora image, and I want a bash. I thought, yeah, let me just make sure that I'm using the proper. It's interesting because I thought that I had this image before.
Yeah, pull the image.
Yeah.
Maybe because it's latest and.
Let me try another image that I have here. It's CentOS. CentOS, I have it locally. So if I do a free-8, I'm seeing the 1 gig memory of the host. Okay. Now let's try something different. Let me specify if I do a Docker -8 and if Docker run -8 or --help in this case, I have a parameter here. let me get it, -m, which specifies the memory limit of the container, right? So I will run the same container with -m 150 megs. Okay, so now that if I run 3-8, what do you think that it will show? 1 gig of memory. That's right. It's just like Bert said. Even this Linux tool was not prepared for containers. Okay, so let's keep playing. Let me run here instead of a CentOS image. Let me run the JBoss Wildfly image. But instead of 150 megs, I will just use 50 megs. Okay, so we know that the Java, the JVM does not look at this information here from the container. So it should think that it has 1 gig of memory. So if I try to run this application, let's see what happens. But let me just stop it because I don't want to RM, and I will give it a name, my Wildfly, because I want to inspect what happened to this container. So let's see it starting. You can see in the Java opt that it has a maximum of 512 megs, and you see that I specified the memory limit, and JBoss process received a kill signal. Let's inspect this container here. Let's inspect my Wildfly. So the problem is that when the process uses more memory than it was limited, it receives a kill signal from the kernel. We can see that when we run the command docker inspect and the name of the container. You can see the state here. The status is exited. It's not running. But you can see also this flag here, OOM killed true, which means out of memory killed. The Java application tried to use more memory and it received a kill signal. That's why when you, let me remove the container here, my Wildfly. That's why when you try to start an application that uses 512 megs, it receives a kill signal, okay? But okay, we can play a little bit more with this kind of application. Okay, I have here Spring Boot application, a very simple one, that when I invoke this endpoint here, /memory, it will start to allocate memory until it will create several strings using string builder, and when it reaches 80% of usage of memory, and you can see here runtime get runtime, and you can see that it reads the total memory and also the max memory. Let me see, where is it? Yeah, here, max memory, those APIs. When we reach the 80% of allocation, it will exit the loop and print the message. Okay, so let's run this application here. So basically, I'm running a container with this Spring Boot application, exposing the port 8080, and I called it my container 150 because I'm limiting the memory with 150 megs, okay? And another thing that I want to show you is that it's using the OpenJDK image as a base image, okay? So I used this image, I exposed the port 8080, and it runs the Java with the print flags final and print GC details just for us to explore this application, and dash R and the name of the fat jar. So when we can see here the Spring Boot application is starting. And now that it started, I can do I can, for example, do a crawl HTTP. Let me get the Docker machine IP of this Docker 124. Let me increase the font size here to help people who are far behind. On port 8080, and I will access API memory. Okay, we can see here the logs starting to allocate memory. Allocated more than 80% of memory. 2015 megs, and the max allowed JVM size is 241. It's allocated 2015. But the application is still working. But we can here extract at least two questions. Why it said that the max allowed memory in this VM is 241 megs? If we specified, okay, we specified that the container uses 150, but we know that the JVM doesn't look at it. In fact, what happens is explained in the JC, the garbage collector ergonomics of the JVM. By default, the maximum heap size of a Java application, if you don't specify that, is to use a smaller of 1/4 of physical memory. So our machine has 1 gig of memory. So it will use approximately 250 megs of maximum heap. Okay, that's why it created, it allowed us to allocate the maximum of 251. But I have another question here. Remember that we specified that the memory limit is 150, and in fact it allocated 215. How was that possible? We saw that when the Docker when a Java application or any process tries to allocate more memory than the limit, it gets killed. We saw that. And how a 150 megs container allowed me to specify to allocate 250 megs? That's another good question, right? But let me show you what happens here. The fact is that, let me run the CentOS container. When we run a command with -m 150, in this case I will not be able to show because the free shows just 1 gig. But what happens is that it creates 150 megs of memory limit plus 150 megs as a swap, as a swap space. So in fact I have 300 megs to allocate, 150 megs in RAM and 150 megs in swap. I could specify, for example, let me do docker run --help. Memory swap. I could specify a memory swap here and say, okay, I want a memory swap of 10 megs. But look how Docker behaves. It says the minimum memory swap limit should be larger than the memory limit. So you, every time that you specify 150 megs, you have 300 megs of available memory. Okay? So I can't. The only thing that I can do is, for example, specify -1, which means no limit for the memory swap, but I cannot have a swap smaller than the memory limit. But let's continue exploring, doing more experimentations. Um, so we know that we could run a container in 150 megs because it really means 300. But what I will do now is suppose that I move this application to a larger host. So I have here Docker machine ls. I have here another machine with 8 gigs of memory. So let me use that. Docker 892. Okay. Docker machine SSH Docker 892 3.8. So we have 8 gigs. So now let's do more. Let's be more audacious. So I run a container with, let me see, with 800 gigs of 800 megs of memory. Okay, I have 8 gigs. So supposedly, I would be able to run my Spring Boot application, right? So let's run it. Let's wait for the application to start. Now we have 800 instead of 150. And now let's use the API memory endpoint again to start allocating memory. And let's see what happens. Allocation failure, and empty reply from the server. The process died. So I gave more memory on the host. I gave 8 gigs instead of 1 gig. I gave more memory. I gave 800 of memory limit, and the application died. I increased the memory, and the application died. So it's really a problem for us who are moving our Docker application to a production host. And that happened because, let's explore that. When I say that the memory limit is 800, in fact I have 1 gig and a half, 1 gig point 6 of memory available. But the Java ergonomic thinks that I can allocate 2 gigs because the default is 1/4 of the memory of the host. Because I didn't specify the -x for the heap, it tried to allocate 2 gigs, but 2 gigs is not available. It will allocate the 800 of the memory, 800 of the swap, and it will get killed. There's no more space. The process dies. Okay? So what's the proper solution for that? The proper solution would be use Java options in the parameter of the Docker file. Okay? Because with the Java option, you can specify how much memory you will use. So I can, for example, run the same memory limit, but I can specify the Java options to have the maximum heap size of 300 megs. Okay, that's one possible solution. And of course, I can run that multiple times, and I will not have that kind of issue. Docker logs, my container, 8 gigs, and I can run the application here, and we will see that it will work because I'm limiting manually. But we can get better. Remember the slides that we said that one of the possible solutions is to use the fabricate image. I have also here in my Docker file one image that uses the fabricate base image, and you can see how simple it is. Because if I specify the from, I just need to specify what's the name of the jar, and that's it. That will automatically use this calculation here of the CPU limit, core limit, and max memory limit, and set automatically the maximum heap size for you. So let me get one example here. Let me run Docker run. I will rm the name of the container using the fabricate base image. If I don't specify, it will run just the Java class path and .jar. But if I specify a memory limit, for example, memory of 150 megs, I just did that, and it automatically executed with the XMX of 75 megs, which is the half of the memory of the limit of the container. I can go even further. I can specify 1 gig of memory, and the image automatically sets to 512 megs. So this fabricate image really helps us to adjust itself based on the memory limit of the container. Okay, and to finalize our last minute, let me just show you what happens when we try to run OpenJDK with a memory limit of 100 megs. You can see that in this environment, it got almost 2 gigs of memory estimated, okay? But if we use the OpenJDK 131, and if we enable to unlock the experimental features and use the cgroup memories limit, it will do the calculation properly. Okay?
Awesome. So I know we're about out of time. We won't have time for questions specifically. She'll open that door in the next minute or two. But what do you guys think about this? So our whole purpose of this presentation is to give you this new idea. You've been a lot of people running Docker already, but maybe running around with sharp scissors and running a little unsafely. Now you have the idea of what the JVM is really doing. The presentation is yours to keep. Can you bring up the last slide that has the link on it again? It has the bit.ly Java Docker fail. Do grab those slides from us and make sure to grab all these presentations. So it's at the top right corner there, Java Docker fail. That'll give you access to the slide deck, give you links to everything you need, and Raphael and I will be available later on for questions. So thank you guys so much.